Okay. So 3.42, here's a reaction. You go from an alkyne to alkyne anion, you see a base amide. And the question is asking, would ethanol be a suitable solvent, right? For this, take a minute to draw this reaction on your notebook. And you would use a pKa value of ethanol and acids in the reaction, right? So let me copy this reaction to my note here. .42 from the back of chapter 3. The reaction is this. Plus NH2 with a negative charge gives the conjugate base and a conjugate acid NH3. The question is, can you use ethanol as your solvent? What I would do is I would look at the pKa's of all the acids in the reaction, right? And the pKa of this acid what is it? 25? 25. And the pKa of ammonia is 38. And based on that, we know the reaction would mostly go forward. Now, what's the pKa of ethanol? pKa of ethanol, that's this, alcohols and waters are together, right? Close to 16. pKa is equal to 16. Now, this is the base you put in your flask. At the beginning of your flask, before you run the reaction, you have three components, two reactants and a solvent. Right? These are in your flask at the beginning. Now, if it's a base, and you have the base has two choices. It can deprotonate the pKa 25 proton or the pKa 16 proton, which is more favorable. The base attacking this proton or the base attacking this proton, which is based on pKa of these two, which is more favorable. Which is more acidic. Which proton is more acidic, basically? Right? Alcohol's proton is more acidic. So if you have alcohol in your flask, the NH2 minus would prefer to remove the more acidic proton first, right? And the reaction product will be different. So what's the answer to this question? Ethanol is not a good solvent for this reaction. Right? Ethanol is not a good solvent for this reaction because it's too acidic for the NH2 minus. pKa is 16. So my answer would be no, because ethanol is more acidic than the reactant acid alkyne. Now, my next question, which is not in the textbook, but I'm asking you, can you choose a good solvent for this reaction? If ethanol is not the right solvent, can you choose a good solvent from your pKa table? A solvent should be a neutral molecule. How many options you have in your pKa table two options, right? So neutral molecules which are less reactive than this, right? Neutral molecules that are less reactive than the pKa 25 and less reactive than the pKa 38. Basically below the line of these two. Right. So in your mind, you should keep this solvent should be the least reactive out of all acids in your flask, out of all neutral molecules in your reaction. Solvent should be the least reactive. The synonym for least reactive is weakest, right? Weakest acid or weakest neutral molecules. It could be a base. Okay, so I would go with this molecule or this molecule from your pKa table. That's a bond line structure. I don't think I need to draw the CH2s because that's understood. Or you can choose hexane. If I, for example, in the quiz, if I gave you an option to choose ethanol or what's this one, butane or propane, you would go with butane, propane, or hexane. Very similar to this. Right. That's a good solvent. Hexanes. We use hexanes in organic lab. We use propanes in our home. That's a gas, right? Propane gas. Gasoline. Gasolines are mostly octanes. Okay, moving on to next question. 3.42. Okay, so without looking at pKa table, determine if water is a suitable proton source, basically acid. If water is suitable acid to protonate this compound, right? I mean, we skip it. That's go back to this. We skip a little topic in this chapter called counterions. We have a counterion sodium, right? That just stays there. It doesn't do anything. The base part of this molecule is the benzoic acetate, right? Benzoate with a negative charge on the oxygen. The sodium is just a counterion. If you want, you can read this section 3.9 counterions. It's small half-page or one-page section that talks about why we put sodium next to a negatively charged compound. We either put sodium or potassium most of the time. Sodium or potassium, they're just counterions. They don't do anything. Make that negatively charged molecule stable by making ionic bonds. Okay, now, so from that, we know this is a base or a negatively charged molecule. Let me copy this down. .43 from the back of chapter 3. Benzoic this is benzoic acid. You know, this is on the not on the pKa table, but a similar functional group is on the pKa table. The question gives this molecule, sodium benzoate, with a negative charge on oxygen and a positive charge on sodium. Right. So whenever you put sodium or potassium, the bond between the organic part of the molecule and the metallic part of the molecule is an ionic bond. Okay, now is water a good source? So basically, they're asking, can water act as an acid to push the reaction forward? When they say good source, right? Good stands for a forward reaction. Can water provide a proton and push the reaction forward? Okay, now what do you think? Complete this reaction, use your mechanistic arrows, draw the products, and predict the direction of equilibrium. Right? At this point, I'm going to erase this forward arrow and let you decide the direction. Draw the products first. Base taking a proton, okay. That's your product, conjugate acid plus hydroxide with a counter ion sodium. Okay. Now, the book also said, do not refer pKa table, right? What do you think about the direction of equilibrium based on the qualitative analysis, the ARIO analysis? When it comes to the ARIO, we compare the stability of two bases, right? We will circle the two electrons that you want to compare. I'm erasing this for now. Okay, we're comparing the stability of this lone pair versus one of the lone pairs on the hydroxide. Compare, oh, you should correct me. This is not the acid. The acid is water. This is the base. Okay, so when it comes to ARIO, you're comparing the stability of bases. To be exact, you're comparing the stability of this lone pair. Right? So which lone pair is more stable, the one on reactant side or the one on product side? Use your A or IO factor. Can you use A factor to compare the lone pair? The lone pair on the reactant side is on oxygen atom. The lone pair on the product side is also on oxygen atom. So it's a tie. Now move on to the next factor. Lone pair on the reactant side has a resonance possibility because that's allylic. This is an allylic lone pair. It moves to the oxygen, moves back and forth, so it's delocalized. The lone pair is delocalized. And on the product side, the lone pair is localized. Delocalized lone pair is more stable than localized lone pair. So label your reactant side as more stable side. Right. More stable reactants. Is the reaction good reaction if the reactants are stable? No. So let's put a cross and fix the direction of arrow, longer backward and a shorter forward. Fine. And the answer to the question is no. H2O is not a good proton source. proton source, aka acid. Proton source means acid. For the given base benzoate or benzoic benzoate is benzoic acid without the proton. Okay. Now, let me ask another question. Can you use your pKa table to validate this? This is our prediction, right? The direction of arrow is our prediction. Can you use the experimental data to see what scientists have observed in the past? This is correct? Okay. When you use the pKa table, you'll be comparing the strengths of two acids. The strength of water is pKa 16 or 15.7. Strength of this proton in a carboxylic acid functional group. What's the pKa? pKa 5, right? So that's the strong acid, stronger acid. And water is more stable or weaker. So that validates our direction of arrow, right? And to go further, how much, what's the equilibrium constant? Or how much of the backward reaction is favorable? Give a number to this arrow. Calculate KEQ for this reaction. What's the KEQ of this reaction? When it comes to KEQ, you would subtract the conjugate acid pKa, conjugate acids pKa from the acids pKa. So 15 minus 5, or 15.7 minus 5, let's round up to 60. Is equal to positive 11. Oh, this is actually pKeq, right? pKeq is positive 11. KEQ should be 10 to the power negative 11, right? Negative 11, or 1 over 10 to the power 11. That's how much product and reactant in your flask. Concentration of product and concentration of reactant. For every product formed, we have 10 to the power 11 reactants still need to react. Okay, so that's the complete review of this type of question. Actually, touches all the sections in this chapter. Qualitative, quantitative, direction of arrows, the position of equilibrium. Okay, let's move on. I'm going to post this notability as PDF on Blackboard. 3.44. Okay, so basically, write an equation for the proton transfer reaction that occurs when each of the following acids react with water. In each case, draw curved arrows and show a mechanism. I think that's too simple because they're all strong acids, HBr, sulfuric acid, and protonated acetone. Let's just choose one and quickly draw that. let's choose this protonated acetone and reacts with water. Okay, let's draw the curved arrow from the base to the acid. Okay, for the backward reaction, the question did not ask this, but I'm still drawing the curved arrow for the backward reaction. The microphone not working. Yeah, it's supposed to have a positive charge. So okay. There should be a positive charge on the hydronium ion. Now, again, the book did not ask, but I'm still going to predict the direction of equilibrium, the position of equilibrium. pKa of this acid, I think it's negative 7.3 on the table. I'm going to round off that to 7, negative 7. pKa of hydronium ion is negative 1.74. I'm going to round off that to negative 2. KEQ, pKeq is equal to negative 7 minus negative 2 is equal to negative 5. The difference between these two is negative 5. KEQ is equal to 10 to the power 5, or 10 to the power 5 over 1. Amount of products over the amount of reactants. And this tells the equilibrium should favor forward. KEQ is greater than 1, so the forward reaction is more favorable. Now let's go qualitatively. Can you compare the stability of the two bases? This lone pair was this lone pair. Which one is more stable and why? delocalized.
Localized.
So it's not allylic, it's vinylic. So the A factor is a tie. Both atoms are oxygen. The R factor is also a tie. They don't have resonance participation. They're both localized. This is vinylic, not allylic. And there is no induction. There is no electronegative atoms. What's the last one? O factor. Hybridized state of the atom in the base, hybridized state of the atom in the conjugate base. What's the difference? Sp. What's the hybridized state of oxygen in water? 2 or 3? Sp3. So two lone pairs and 2 sigma bonds, total number is 4, and it's localized. You don't need to worry about subtracting a p from sp3. So this is sp3. Here it's 2 lone pairs and 1 sigma bond. Static number is sp2. You don't need to worry about resonance. It says sp2. Now, what is the orbital factor in the ARIO says? Smaller the orbital, more stable it is. In other words, sp2, lone pairs in sp2 is more stable than the lone pairs in sp3. So conjugate base is more stable, and that's what the direction of arrow indicates, right? So you can say this, the product side of this reaction is more stable, and it's a good reaction, forward reaction. Okay, moving on. And you can do this to any compound. If you think this is not difficult enough, I can give a different example. You can try all of these. Okay, a similar one, 3.45. I think it's very similar to the 3.44, but they are bases, not acids. On the previous question, we had acids. Now we have bases. Right? They're all anions. Choose an anion that you'd like me to solve. A, B, C, D. Which one you want to try? Hardest. Let's go with C. Right. Okay. 3.45 C. And the question did not identify these compounds as bases. And the previous question, 3.44, they did not say the given compounds as acids. You are the one assigning the role to these compounds. Here is the compound ion, and the question only said that you're reacting this compound with water for a proton transfer. So they chose specific words to not identify given compounds as base or acid, but you can do that. Okay, by looking at these two, you're pretty much sure, because this is anion, that should be the base. Right, more electron density, electron-rich compound, and this is acid. Right. Okay, now draw the product for this reaction and the curved arrows. Right? Start your arrow from the base to the proton on acid and break a sigma bond. Products. Okay, that's a product. And for your convenience, I'm going to put the hydrogen there. I mean, all of the carbons have a hydrogen, but let me only put a hydrogen on that carbon because that's a newly added hydrogen. Plus hydroxide. Acid, base. Okay. Now for the backward reaction, the arrows go like this. And again, in the question, they did not give this lone pair. It is optional to put the lone pair on bond line structures. They did not put lone pairs. But based on the negative charge, you know, a negatively charged carbon must have a lone pair. So I put a lone pair there. Okay, so that's how much the book asks for. But I want to ask you more. Can you predict the position of equilibrium based on qualitative and quantitative analysis? Let's go with a prediction first, and then we'll use pKa table to validate this. When it comes to prediction, we compare bases. Right? Compare the strength, or sorry, stability of these two lone pairs. Lone pairs on carbon versus lone pair on oxygen. They both have negative charge, so it's okay to compare. Sometimes we have a neutral atom and a negatively charged atom. I would not compare two differently charged atoms. All right, they're both negatively charged, so it's okay to compare. Okay, stability of lone pair on carbon versus stability of lone pair on oxygen. What do you think? Lone pair on oxygen is more stable based on the A factor, the atom factor. Electronegativity of oxygen is more than carbon, so let's label this as more stable. A more stable means weak base or less reactive. Right. So the product side of the reaction is more stable. Let's fix this arrow like that. Now use your pKa to validate this one, quantitative analysis. Compare the pKa of water, which is 15.7 or 16, and pKa of the hydrogen on an sp2 carbon. Where is it on pKa table? Hydrogen on sp2 carbon. What's it? 44, right? pKa 44. I would just write it approximate because it's not exactly the ethene. It's a little different compound. So approximately equal to 44. Now that still says this acid is more stable or weak acid or less reactive. And it's a complete analysis. The product side is more stable than the reactant side. And if you're asked how much, then you would calculate the KEQ. I guess the KEQ should be 10 to the power positive 18. That's greater than 1. Okay, it's a good forward reaction. Right. Okay. Moving on to a different question. 3.46, I don't think I need to draw that. Identify the more stable anion, in other words, weak base.
It's 28 on the last big question.
Oh, okay. Yeah, my math. Okay, 28. Good. Okay, so 3.46. What do you think for A? Which is more stable anion, in other words, the weaker base? The one on the left or right? One on the right. Why? It's delocalized, right? The negative charge on this carbon, basically the carbon has a lone pair, right? They did not show that, but you should know there is a lone pair. That lone pair is allylic and is delocalized and more stable. Right. How about B? The one on the left or right? Which one is more stable? One on the right. Why? So because it's on the negative charge or the lone pair is on more electronegative atom nitrogen. So the first one is the R factor, second one is the A factor. How about third one? C. Still one on the right because of the O factor, orbital factor. Sp orbital holds the negative charge better than sp3 orbital. Right, so good. 3.47. For each of the given compounds, identify the most acidic compound without pKa, without the help of pKa. Right? So basically, they're asking you to use your prediction or qualitative analysis. How about A? Which one is the strong acid? One on the right, right? The thiol, SH, the hydrogen on sulfur is more acidic because removing the hydrogen will put a negative charge on sulfur. Sulfur is a larger atom, the A factor. Right? So when it comes to prediction, these are acids. You must draw the base to compare. Draw the base of this alcohol, cyclohexanol. Draw the base of cyclohexane thiol with a negative charge on oxygen and negative charge on sulfur, and that's when you compare, right? How about B? Phenol and cyclohexanol. Which one is more acidic? Phenol. One on the left, phenol, right? Because losing the hydrogen will put a negative charge on oxygen. That's allylic. And the lone pair on the new lone pair on the oxygen would be allylic. But on cyclohexane, you don't have the resonance possibility. So here it is the R factor. A is a die. So we go to R factor. Phenol is resonance stabilized. The conjugate base of phenol is resonance stabilized. How about C? you have a lot of chlorine here, and on the right side, you have methyl groups. So draw the conjugate bases, remove the protons on both, put a lone pair and negative charge on the oxygen. Now compare which lone pair is more stable. One on the left, which factor? Induction factor, right? A lot of chlorines will stabilize the negative charge on the oxygen. So losing this proton is beneficial. Okay, about D. One on the left. So losing the hydrogen on the nitrogen, we'll put a lone pair on nitrogen. Here, you will put a lone pair on the carbon, right? Any questions? You should ask a question here because this is one place where pKa table and prediction are different, right? We talked about that in the last class. Only one place the pKa table follows a different trend. They said without using pKa table, so one on the left is more acidic. Losing a proton will put a lone pair on nitrogen. Can you see this by the way? I think it's too small. Here's a nitrogen atom. You put a lone pair on the nitrogen, you put a lone pair on the carbon. So A factor tells nitrogen lone pair is more stable, so the proton on the nitrogen on the reactant side is more reactive. But the pKa table tells you differently. pKa of this hydrogen is 25, pKa of this hydrogen is 38. So this is more acidic. That's the right answer. But without looking at pKa, anyone will tell nitrogen, proton on nitrogen is more acidic. Okay, so I think they all follow the similar trend. If you look at this one, acetone versus propane. On the pKa table, you can compare without pKa table. Losing a proton from here puts a negative charge and lone pair alike, more stable. So this proton is more acidic. pKa table does the same thing. 19.2 for this proton, 50 for this proton. Okay, so let's move on. I think we did a lot of examples similar to this. Draw the reaction, draw the mechanism, predict the position of equilibrium based on qualitative or quantitative analysis. Let's go. Let's look at D. Right. D here. So this is an intramolecular reaction. Sometimes the reaction can happen inside the molecule. You don't need an acid or base to come from outside the molecule. Right. So that's a reaction with a negative charge and oxygen. The reaction mechanism would go like this. This is the acid part of the molecule and base part of the molecule. So intramolecular, inside the same molecule, we have acid and base. Start the arrow from base to the proton on acid for the backward reaction. Now, you can use your A or IO factor to predict the direction of equilibrium. What direction is more favorable, forward or backward? Forward, right? Negative charge on oxygen is more stable. this part. When product is more stable, the reaction would go forward. And you can check the pKa if you want. pKa of alcohol is 16, pKa of ammonia is 38. At 38 versus 16, this is still stable. I think your quiz will be similar to this one. I don't see any. Maybe it is one question. I gave 6 or 7 compounds and asked you choose, ask the students to rank the compounds in terms of acidity, right? 6 or 7 compounds, rank them based on acidity. Let's see if I can capture that.